Start the, I'll just run and grab it real quick.
$24.
Okay. Large and extra large?
Mm-hmm.
I got this, go, you go ahead and start, I'll be right back.
Okay, well, let's go ahead and pick up where we left off last time. So we wrote last time that the general state of the spin of an electron is given by a state vector, and we had two states. If we had an SGZ apparatus, for example, we could write the state in terms of the Z basis. Okay, and we can also write this state in the X or Y basis. So this is the same state vector. And I can write it as Cx plus x plus and Cx minus, where these are coefficients now in the X basis. And we can also write the same state vector in terms of the Y basis as Cy plus Y plus Cy minus Y minus. Okay, let's see, the Z basis is Z plus and Z minus, there's Kets. The basis here is X plus and X minus, and the basis here is Y plus and Y minus. And the coefficients we demand that this state vector, this is the same state vector in all three cases, it's just written in different bases. This is equal to 1. We have the magnitude of C1 squared plus C2 squared is equal to 1 when we're discussing the Z basis, or we have the same set of relations in any of the separate bases. They must all have these coefficients whose magnitude squared sums to 1. Okay. Now let's discuss the amplitude for the outcome of a measurement. So let's consider the amplitude. Z plus psi. So this is an inner product between the state vector and this basis vector. And so from the definition that we wrote down over here, this amplitude has a value. If I take the inner product on the left here with Z plus, then it will hit this Z plus and give me 1. So I'll have a coefficient C1, and then Z plus with Z minus will be 0, so I won't get any contribution there. So this will just be C1.
And that Z plus would be like the conjugate, right? So that would be.
This is the bra vector Z
Yeah.
plus.
Yeah.
Okay, so the state vector psi has this coefficient C1. That the fact that I'm coming at it.
Oh,
on
I
the left
got it now. Okay.
does not conjugate anything.
Gotcha.
Okay, so this is a complex number, a complex amplitude. And if we have, we demand this is the case, that the inner product of psi of itself is 1. So we can, we said before that mag C1 squared is a probability. Okay, and this is, it is the probability that a measurement will find the particle in state Z plus. Okay, and the expression magnitude C1 plus squared plus the magnitude of C2 squared equals 1 is a statement of the conservation of probability. The total probability of all possible outcomes has to be 1, because something has to happen. Okay? Okay, so let me be very hyper-specific here about what quantum mechanics says. So this is an important point. Consider a collection of electrons, unpolarized electrons. So suppose they're from an oven. So I have, let's say I've got an oven here, and I've got these electrons that are streaming out, and I have my SGZ apparatus here. This is a big misconception that many people have. A lot of people will say that, I've got a bunch of electrons here, that C1 squared of them are spin up, and C2 squared of them are spin down, because it's a probability. So what's wrong with that statement?
It's not actually that, it's not the number of electrons you find in those states. The square is the likelihood that you'll find electrons in that state.
Right. But again, that's not specific enough.
They're not in that state until you measure it.
They're actually, didn't you say earlier that they were in both states?
Right, they are. So
Oh,
this
is before the measurement.
the electrons are in the state, they're in the superposition of states. They're in this state. This is a superposition of states. They don't enter a state Z plus or Z minus until you measure it, okay? So it is not the probability that, it's not like, let's say it's 50-50, or let's say it's 60-40. It's not as if 60% of the electrons are spin up and then 60 are spin down, and so they go through the apparatus and then you get 60%, 40%. Okay, I'm just emphasizing this again and again. That's not the case. They are in the superposition of states until you measure it. So the really important part of the statement is that C1 squared is the probability that a measurement will find the particle in the state, because it is in the superposition beforehand. Okay? So that is a common point of common misconception. Okay. Then upon measuring, so it's upon measuring, so we'll talk about different kinds of measurements, on different kinds of particles. When you measure, you jump into one of the basis states. Yes?
So, how would we be able to tell the difference between a particle with a hidden value that we don't know until we measure it, and a particle that is in the superposition? Does that make sense?
What's a particle with
So-
a hidden value?
Well, I was saying, like, what you were describing in the beginning is like these particles have a hidden value that we don't know until you measure it. But what you're saying is that it's either of those values at the same time.
Right.
And so, like, I've heard that, like, some we've been able to make bigger and bigger particles have superpositions, but like, what would, I guess I'm not quite understanding, like, what makes something have a superposition instead of having it like a value that we don't know? Or is that a matter of philosophy?
You mean like what particles can we put?
Like, how do we know that it's the measurement that makes it jump into a state, and that it wasn't in a state already before we measured it? Because, like, if it's the
Because
measurement that
I
lets you
believe
know.
There was an experiment that showed that the state it goes into and affected by, the way you measure it?
Yes, that was the the Stern Gerlach X. Like those are the 3 experiments you showed us the other day.
Well, okay, wait, to answer your question about, say your question again and all.
I was sorry. I was just trying to reword what I thought he was asking.
what
Like,
is it?
how do you know that it is in a superposition until you measure it, as opposed to the other way where it's in a state and then you measure, like, how? Because you don't know until you measure it, right?
Okay,
So
well, that's a good question, very good question. It's interference patterns, for example. So if I have an electron, so if I have just, now I'm not talking about spin here, we're talking about position. But if I have, an electron wave that goes through 2 slits, and then I have a screen, the measurement here would be where's the position of the electron, for example. We don't actually, in this particular case, we're not going to measure it, but the fact that it can interfere with itself tells you that it was in a superposition.
Okay, that's kind of what I was asking.
So, we can do things with the electron, which we'll discuss shortly, which shows that it's interfering. Until you take a measurement, you jump it into that state when you take the measurement. But before that, it has the possibility of being in both states and can do
Interference.
something that only a particle in those 2 states can do.
Exactly. Okay, that makes sense. Thank you.
Okay. Okay, so upon making a measurement, the particle can jump into one of the possible basis states with a probability given by c squared for that state. And this is called the Born rule. And this was the contribution of Max Born. Okay, and so that's how quantum mechanics behaves. Quantum mechanical properties, for example, of a particle behave, and that's the rule that is apparently what occurs. So, this is it's a strange thing to say that the particle just jumps into one of these states, but that is apparently, based on all of the measurements that physicists have done, that's the way it really is. That's the way nature behaves.
is there anything written about thoughts about what it is about measuring it that makes it, like, what mechanism is in place that taking a measurement makes this happen?
Yes, but it's, measurement theory is, what really happens when you take a measurement is very complicated. The problem is that, there was, and there's sort of a philosophical, discussion about what happens when you make a measurement and, what is an external observer. So if I'm the external observer who does something, make the measurement, and then the particle pops into its state, that's one way to look at it, but, and what occurs there is not, this is a rabbit hole that you can go very deep into.
Like, what if you and another guy are making a measurement at the same time? Whose measurement does the thing?
But isn't like measurement, you mean like a machine could also be an observer, right? As long as it's like interacting with the system in some way that can make a measurement.
Yeah, that's a good point. But the issue is that whatever it is that interacts with the system that you're trying to
Becomes
measure,
changed.
it's also a quantum mechanical system. And so it has to obey the laws of quantum mechanics. Right? So it,
It's even true on a macro scale. If you think about it, it's like you're measuring the temperature of something. in the act of measuring that temperature, it must change the temperature of that object, right? Like as if, heat would transfer.
Sure.
So
yeah,
like
yeah,
it,
yeah.
that measurement issue is true on even a macro scale.
PBS actually has a pretty cool
Yeah.
episode about that on YouTube.
Also, like how you can't measure the speed of light directly because like the things that happen when you're trying to measure it will change your measurement devices.
So, well, okay, so let's just, it's a really interesting area, but it would take us really, in a different direction. But it is an important question. I don't, at this stage, it's not useful for us to talk
Right.
about it until we've sort of learned the mechanics of how quantum mechanics works.
Okay.
And then we can start talking about it. But it gets, it is interesting, and people have added layer upon layer upon layer. So you have an observer who watches an observer who watches an observer. So you can really get into the details there in the weeds. But anyway, okay. So that's kind of the way it works. And let's just we're going to go with that because we're not going to talk too much about measurement theory. So now let's kind of discuss the linear algebra of what we've written down. And what we want to do now is be able to find these different coefficients in terms of the other ones, because we want to be able to switch bases. Okay, so let's discuss what's called the completion of a basis. So this is just some linear algebra. So a complete basis is just one where I can decompose any vector in that basis. Okay, any vector in the space. So let's do this with, before we write it down in Dirac notation, let's just do this in kind of awkwardly in the notation that we learned for two-dimensional vectors or three-dimensional vectors. So let's write V as I can write V like this, right? This is just, everyone's seen that before. Everyone's comfortable with just that notation. And so now let's dot through with E1. So I'll have E1 hat dotted with V will be V1, then E1 hat plus V2, E1 hat dotted with V2 plus, right? So now which terms go to 0 here?
E2 and E3.
These ones will go to 0, right? Because E1 and E1 is perpendicular to E2 and E3, and this is just 1. So we can write that V1 is equal to E1 hat dotted with V. Okay, and we can also write that V2 is E2 hat dotted with V, and V3 is E3 hat dotted with V. Right? So we can write that. So now let's rewrite our equation for the vector. So I can write this then as, I also want to swap this E1 and this V1, okay? So I'm gonna write E1 hat, and then in parentheses here, I'll put V1. That's E1 hat dotted with V, plus E2 hat, and then E2 hat dotted with V, and then E3 hat dotted with V. Okay, this is kind of an awkward way to write it maybe. But then I want to write the right-hand side as an operator, acting on V. So we can write that V is equal to, and this is going to be weird, okay? So this is a really strange thing to write, but just think of it this way. E1 hat's it's gonna eat, it's like looking for a vector to eat. It'll dot into it, and then whatever's left will be pointing in the E1 hat direction. Okay, and we'll do that for each of these. Okay, so we've abstracted this thing into this object here, and now notice that I have a V on both sides. So there's no content, you know, I can get rid of the V on both sides and just write this as 1 equals E1 hat dot plus E2 hat dot plus E3 hat dot. Okay, this is called a completeness relation. All right, any questions about that? So this is, we're going to use this kind of thing repeatedly. I'll rewrite this in Dirac notation in just a minute here, but does everybody understand the concept here? What this says is that I'm able to write 1 in terms of a set of basis vectors here that are arranged in a way such that it's an operator. Okay, so E1, E2, and E3 are the basis for the 3D vectors that we know. So for the two-dimensional spin space of the electron, we can write the following. 1 equals Z plus plus Z minus, okay? So these are our two basis states for the electron, Z plus and Z minus. So what I've done, this ket is like this E1, and Z plus is the sprawl vector, and that's like the E1 with the open dot here. Okay. So let's just write psi equals psi, this is just an identity. Okay, and let's use this relationship. So 1 on psi, I'm gonna use the 1 here. And then I'll use this side down here. So I wanna put this 1 right there. So, and I would put then z plus, I would write it this way. Okay?
Okay.
Now, let's let it act. So this is z plus, and now what do I have? I've got the amplitude z plus psi. Here, but this is just, we wrote down, this was just C1, and this was just C2. So we have psi is equal to C1 z plus C2 z minus. Okay, so this is just notation, but it's something that this is a really very common trick to use when you're doing quantum mechanics. So you'll see it very frequently. Okay, now, are there any questions about that?
I guess I see why you use that, because at least it looks like it makes more sense than the other one. That open dot really throws me off.
Right. This is another good, reason for Dirac notation, so that you just get the amplitude, and it's a pretty nice thing. Even, it might look a little awkward, but you'll get used to it after a while. Okay, now, before we get to doing a bunch of basis changing and things like that, I want to show you, this is something that Feynman did in the Feynman lectures, and it's really clever, and I wanted to just show it to you. Okay, and so you can derive this expression by just doing Stern-Gerlach experiments. Okay, so let's just take a few minutes to do that. Okay, so to do this, Feynman described what he calls a modified Stern-Gerlach apparatus. And so we're in our original Stern-Gerlach apparatus, if we just had an SG, we had one pole of the magnet here, and we had one pole of the magnet here, and that caused this inhomogeneity in the field. So that was SGZ, say. So if you take, and that when the beam comes in here, classically it does this. The beam splits like that. And what Feynman said was, well, let's flip the magnets and make them twice as long. So he has So when they come into this they come into, to this part of the apparatus, the beam it'll start tipping the other way. It's gonna start trying to bring the beams back together. So this just replaces, if this is north and this is south, this is north and this is south. And then he puts another regular Stirling Gerlach thing here, magnet, that takes these beams and brings them together, and this will just be a regular piece. Okay, so this whole thing is the modified Stirling Gerlach Z apparatus. Okay, so these are all the magnets are in the Z direction. So the beam of electrons, as it goes through the apparatus, it comes apart and then it comes back together, and so you can basically bring the beams back together again. Okay. So this one would be an open apparatus where you don't, no blocking of beams. And then you can also make one here that has a block in it. So you would put a block there, and this would select, say, the Z plus only. So. Okay, so then we can look at the probability of we can just consider the following probability. The following experiment. So let's put say an SGX apparatus here, and then we'll put a modified SGZ. And then we'll put another SGX over here. So if we have an unpolarized beam coming into this SGX apparatus, and we take the X plus beam that comes out, and then it goes through our no blocks, so there's no blocks here at all. And it comes out of the SGZ with no blocks, this modified SGZ, and then what do we get? Well, it turns out that you'll find you get only X plus and you get 0 out of X minus. Okay, so remember we said before, when it goes through an apparatus, it destroys the information, right? So if we had a Z beam or an X beam here that went through an SGZ apparatus, it should split it into 50-50. Okay. So we send it through an SGZ apparatus, and then we let it come back together, and we remeasure SGX. And now it's pure SGX again, it's not a quarter. Okay? So we can calculate the amplitude for this process. So there are has two terms for the two paths. Okay, so we're starting here at X plus. We can take path 1 which is through Z plus, or path 2, through Z minus. So on the top path, we'll go through Z plus, and then Z plus back to X plus. So this is path 1. Oops. Plus, and then now we'll just go through X minus, or sorry, X through Z minus. Okay, and this will be path 2. And because we get 100% of the, if we sent in 0 here, we get in 0 out. Okay, so that's just an experimental fact. And since we're writing the amplitude this way, we see that we have X plus on both sides of this thing here and X plus on both sides of this thing here. So we can take the X plus out, we can pull it off from the left side here and just then write Z minus plus Z plus X plus equals 1. Okay, and for this to be 1, this must be 1. Okay, because we know that X plus, the inner product X plus is 1. So in order for this expression to be 1, that means the stuff in here has to be 1. And so we recover this, we recover the completeness relation. Yes?
So, in that diagram where you write no, X plus 1 state, does,
In zero.
oh, in 0, okay.
Yeah, sorry.
Okay.
In 0.
Alright.
Okay, I think that's a really interesting way to come to this completeness relation. But again, Feynman had all sorts. He just had a very interesting way of looking at things, and so I wanted to share that with you. I think the book does it as well, but it's out of Feynman's book. So. Okay, so let's talk about switching bases. All right. Let's do this by example first. So by looking at real space vectors first. So if I have two sets of coordinates, so I can say this is X and Y, and then we could have X prime and Y prime coordinates. Then when I draw in a vector, here, let's see, I can, let's just take one, well, yeah, let's just take one. Right along the x prime direction. So we can write V as V1 x hat plus V2 y hat, or we can write this also has to be equal to V1 prime x prime hat plus V2 prime y prime hat. And if there's some angle theta between the axes here, we know how to do this. This is just a rotation. So we can write x prime hat in terms of x hat and y hat. Right? So we can write x hat prime will be, let's see, I'm doing this right. It's, cosine theta x hat plus sine theta y hat, and then y hat prime would be minus sine theta x hat plus cosine theta y hat. Okay, and I'm not sure if I got my theta. I don't know if the minus is here or here. Let's see. X prime hat. Yeah, we'll start off at one. Yeah, okay, but then it goes. Yeah, okay, that's right. Okay, so this is the kind of transformation we're gonna look for. We want to look for transformation between the basis vectors. And that's because if I plug in now for x prime hat here, if I plug in this expression, and then I plug y prime hat in terms of y hat, then I can solve for v1 prime in terms of v1 and v2 and so on. Okay, so that's what we want to look for. Now the only problem is this is not, the vector spaces we're dealing with now are complex, and so it's not as obvious here. It's not, we are not doing a simple rotation like this, and we'll see that it's much different than a rotation in real space. So we have we saw from one SG experiment that we could write z plus is equal to 1 over the square root of 2 of x plus plus x minus. Okay? But in general, we have to be, in general, we have to work this out mathematically. Now we have some freedom, of course, in picking coordinate systems like we normally do. So there are some conventions, and we'll follow the standard conventions when we do this. So if I want to write, let's go ahead and let's see if we can write in general terms here. Let's write 1 over the square root of 2, and then I want to put an A here for x plus, and b for x minus. Okay, because we only, this is just z plus, we wanna find z minus in terms of this, so let's be general here. Okay, so now we wanna write this, and then we'll use the relations that we found yesterday. In particular, the z plus has to be 1. We need this in particular. And we also need z plus and say x plus. This was from the experiment that we did before. This is 1 over the square root of 2, right? Because let me put this in, let's offset it here. This was from an experiment, so if I had a z plus electron, I know that the inner product, if I take the inner product with x plus, I'll get 1 over the square root of 2. Okay, and also in particular, I could write this as this squares a half. Okay. All right. So let's use the top relationship. So z plus is equal to, that inner product will be 1/2. And then you want me to work this out by taking the bra vector, or is everybody comfortable with taking the bra vector and just doing the? Well, let me do it. Let me do it this way. Let me be specific here. Let's choose a equals 1, and then I have some freedom to make these choices here, and b equals e to the I alpha. Okay, so I'm just picking something with a phase here because it's going to come in a little bit later. This is, these choices here, you can leave it completely arbitrary, but I'm simplifying it a little bit now so that you don't have just a mess of things to deal with later. Okay, so if we take this inner product with itself, then this will give me, I'll have 1/2 from 2 factors of 1 over the square root of 2, and then we'll have x plus a is 1, plus e to the minus I alpha x minus. So that's the bra vector that I'll make from these, and then I'll have just x plus e to the plus I alpha x minus. Okay, so this will be 1/2, and then from the 2 x pluses, I'll have 1, and then x plus x minus will give me 0. This x minus x plus will give me 0, and then this x minus with this x minus, I'll have e to the I alpha times e to the minus I alpha. That's just 1, so this will give me 1. Okay, so it works as a normalized vector. And now let's write z minus as 1 over the square root of 2 x plus plus e to the I beta x minus. And now we can use the fact that z plus z minus should be 0 to write the following. So z plus, we already turned around z plus into a bra, so that's this. So we'll have, this has to be 1/2, again, from these two things. And then we'll have x plus that hits this x plus and gives us 1. Then we'll have this x plus will hit this x minus and give 0. This x minus will hit this x plus and give 0. And then this x minus will hit this x minus and give us plus e to the I beta minus alpha. Okay? And that has to be 0. So for this to be 0, e to the I pi is equal to -1. So that means beta minus alpha has to equal pi, and we have some freedom here to choose alpha or beta. We can, make a choice here, and let's go ahead and choose alpha equals 0 and beta equals pi. Okay, so if we do that, then we have the following. Then we'll have z plus is equal to 1 over the square root of 2. X plus plus x minus. And z minus will be 1 over the square root of 2. X plus minus x minus. Okay, so we have the z basis in terms of the x basis. Okay, so this is, that's a really good set of a transformation to remember. And now we can, now that we have z plus and z minus in terms of x plus and x minus, and I can go backwards here by just solving for x plus and x minus. So if we add these, two things together, then we'll have 2 over the square root of 2 x plus. On the right hand side, the x minuses will cancel, and that will be z plus plus z minus. So this means that x plus will be 1 over the square root of 2 z plus plus z minus. And then if we subtract them, we'll have square root of 2 x minus is equal to z plus minus z minus. And so we have then that, let me just write both of them together. So it's x plus, these things are, okay, so they look identical. We're just replacing z with x. Okay, and these all satisfy x plus z plus, if I take the square of this thing, it's got to be a half, and x plus with z minus is a half, and x minus with z plus magnitude squared is a half, and x minus z minus squared is a half. So all of this stuff was from experiment. Okay, and so when we are constructing these basis states in terms of each other, we have to make sure we satisfy these rules. So now let's do y now. Okay, so y won't be so straightforward this time because we already did the simple thing with our choice of coefficients here with x. So for y plus, let's write for y plus in terms of z plus and z minus. We need to satisfy y plus z plus magnitude squared is a half. All of these, let me just write it as y plus minus z plus minus. All these things have to be a half. And we also need them to satisfy y plus minus with x plus minus equals a half, because we've already written x in terms of the z basis over here, so. Okay, so we have a little bit, it's a little bit more constrained here for y, but we'll go ahead and write down the same kind of thing. So let's write I can write y plus in terms of the z basis again as z plus plus e to the I alpha z minus, and let's write y minus as z plus plus e to the I beta z minus. So we're going to try the same thing here and then see what we get. Okay, so these will clearly satisfy the y plus minus with z plus minus is equal to a half. So let's work with the x. So we'll take x plus with y plus. So what will that be? X plus is, it's just z plus plus z minus with the 1 over square root of 2, so it's pretty straightforward there. So we'll get the half because we've got a factor of 1 over the square root of 2 from both of those. The z plus will just give me 1. And then the z minus is going to hit this and just give me 1 plus e to the I alpha. Okay, and so we need the magnitude squared to be, so x plus y plus magnitude squared. This will be a quarter, 1 plus e to the I alpha times 1 plus e to the minus I alpha. That's I'm taking this complex number and I'm multiplying it by its conjugate to get the magnitude squared. And this is equal to 1/4. Let's see, we'll have 1 here, and then I'll have a plus e to the I alpha plus e to the minus I alpha. That's plus 2 cosine alpha, using the exponential notation, right? So cosine alpha is 1/2 e to the I alpha plus e to the minus I alpha. Okay, so we get the 2 cosine alpha from those two terms, and then when these multiply, I'll get another, I'll have this times this just gives me 1. So this gives me, I have 1/4 2 plus 2 cosine alpha. Okay. And then if I take x plus with y minus, structurally this thing is like, it's the same, except I have a beta instead of an alpha. So this is 1/4 2 plus 2 cosine beta. Okay, and then finally we need y plus y minus has to be 0. So this will give us, well, let's go ahead and write it out here. This will be 1/2, and then I'll have z plus e to the minus I alpha z minus, and then I'm operating on z plus e to the plus I beta z minus. So this is 1/2. From the z pluses, I'll get a 1, 0, 0, and then from this I'll get plus e to the I beta minus alpha again. Okay, so so this has to be 0. So I need beta minus alpha to equal plus or minus pi. But I also need to satisfy these two things. So here I need, let's see, what do I need? These things have to be 1/2, so cosine beta and cosine alpha have to be 0. Right, I need, these things must be equal to 1/2. So that means if this term goes away, I'll have 2/4, which is 1/2. So I need beta minus alpha is plus or minus pi, and then I need cosine beta to be equal to 0 and cosine alpha to be 0. So the conventional choice, they have to be pi over 2. So the conventional choice is let alpha equal pi over 2. And beta minus pi over 2. Okay, so if alpha is pi over 2, that's just a 1, and if beta is pi over 2, then that's an I. So then we can write y plus is equal to z plus iz minus. And y minus is z plus minus I z minus. Okay, because e to the I pi over 2 is cosine pi over 2 plus I sine pi over 2 is plus I, and then with the minus it's minus I. Okay, so this is the weird part, we have an I in here. Now we can solve solve for the y plus minus in terms of the z plus minus in the same way. So we can write z is equal to z plus is 1 over the square root of 2 of y plus y minus. And z minus is, there's an overall minus I. Okay, so it is the i's here and the y, the fact that we need an I in here to discuss the orientation of an electron being spin up or spin down in three-dimensional space. That's a very quantum mechanical thing. This is one of the proofs that you need. You can't do quantum mechanics without complex numbers. It's a pretty profound statement. You can't understand quantum mechanics without complex numbers. And this is one way to show it explicitly with the spin 1/2 particle. Okay, so now we have a way to describe the spin 1/2 particles in these different basis states. But I want you to erase any idea in your head that these basis states point along the axis directions in 3 space. Okay, these are not directions in 3-dimensional space. These are abstract state vectors in the Hilbert space. They have nothing. They're related to the 3-dimensional space that we're in, but they do not in any way point along those directions.
They're orthonormal, but they're not like, you can't actually physically think of them being perpendicular in 3-dimensional space.
Right. I mean, these are in an abstract. These are in a different space. These are not real space vectors that you're used to. Okay, well,